G'day, I'm Chris Kohlhoff, author of Asio and Boost Asio.
Hey, and I'm Klemens, and my favorite method of cancellation are segmentation faults.
And welcome to the next episode of Talking Async.
So what are we going to talk about today?
Well, you might remember that in the previous episode of Talking Async, we talked about using C++ 20 coroutines to write async code that looks like simple synchronous code. We also took a look at a brand new feature in Asio that lets us easily run coroutines in parallel.
Well, so we had some magic happening with this thing, that if the watchdog times out, our operations get canceled.
That's right.
And we just showed how that looks in the resulting code, but I reckon people would want to know more about how this cancellation would actually work under the hood, especially if they want to implement something custom.
Okay, well, let's take a look at that. Let's have a look at cancellation in depth and see how all that works. So just a reminder that the code for this presentation is available at the link on the screen right now, and it requires recent versions of Asio, which you can download from the link below. To start with, we're going to use the same example that we used previously, which was a simple proxy. And just a reminder, the overall flow of the proxy was it would first accept a connection up here. And then after a new connection was accepted, it would establish a connection to an upstream server. Once that was successfully connected, it would then initiate two loops which would run in parallel. The first would read from the client and write to the server like this, and this other loop would read from the server and write to the client.
Just to explain that with the previous example, each of those was one of those transfer functions you showed, right?
That's right. And when we got to writing this example up using coroutines, each transfer function corresponded to each of the loops on the screen right now.
Right.
Okay, so let's take a look at the code. As a starting point, I've copied in the code from last time, but the original one that was based around using lambdas. So you can see on the screen right now, for example, here is the code that does the read from the client here. And then once that read is successful, then does the write to the server. And if that's successful, it comes back around to read from the client again. So that's our loop that we just saw. What we're going to start off with is we're going to add cancellation in its most basic form. And this is the way that people have been terminating connections in Asio code since it was first written. And that is, we're going to wait for some timeout, and then we're basically just going to tear down the connections. Let's have a look at how we would do that. So first of all, in order to add a timeout, we're going to need to have a timer in our class here. So let's go down to the bottom of the class, and we're going to add a couple of new data members here. So the first one, we're going to add this time point, which is the deadline. And if there's no activity on the connection before this time, then we're going to tear down the connections. And then we're going to add a steady timer, which will be used to perform the asynchronous wait. Okay, and now let's write a new loop of code that is going to use this timer. So this loop, first of all, it is going to set the timer expiry to the deadline. And then it's going to kick off an asynchronous wait. So what do we do here in this asynchronous wait? Well, when the wait completes, we're going to check whether the deadline has passed. Now, if it hasn't passed, then we're just going to go back around and loop again. So that's just going to call back to continue the watchdog. Otherwise, we're going to stop. We're going to stop the connection. So if we have a look up here, the stop function here just closes the two sockets. Okay, now this is not quite complete. So we're going to have to, first of all, add something that terminates this watchdog loop when everything gets torn down. So we're just going to add an extra check in here so that we don't continue the watchdog if we've already been stopped. And let's add a function up here. And we're just going to use the test of whether or not the sockets are still open to decide whether or not we've been stopped. And finally, to finish this off, well, if we're shutting down, well, we need to stop the watchdog and need to initialize our timer and kick off the watchdog when we start our read and write operations. One more thing is we need to actually set the deadline. So what we're going to do is we're going to set the new deadline whenever we start a read. So let's just say the deadline is set to whatever the maximum of whatever it currently is, and 5 seconds from now. And we'll just put the same thing down here for this read. Should we give that a go?
Well, I think so. I think I called that a blunt tool last time, didn't I?
A blunt tool, a blunt instrument. That's right. Okay, let's copy this to step 1 and make step 1. Okay, there we go. All right, so let's run that. So as before, the arguments for running this program are the endpoint to listen on. So we're just going to listen on this port here and the remote host to connect to, and we're going to use the boost.org web server again. And so now what should happen if we connect to the port? So first of all, if we just make our request, then everything finishes successfully. If instead we just sit there and let it wait for 5 seconds, then everything times out. So just to recap, we have our watchdog, which is performing a loop of asynchronous waits. And all it is doing is checking for whether or not the deadline has been passed. And if the deadline's been passed, then it will stop the proxy by closing the sockets.
Dumb question. Couldn't I, instead of assigning deadline and then checking the async wait, just always call expires at over and over again? Or would that be a race condition?
No, actually, that is a perfectly legitimate implementation approach. But it is more costly because it will wake up the timer every time you modify the expiry. So this...
Oh, so internally it does basically the same thing.
That's right. But by using a separate member variable for the deadline, what we're actually doing is minimizing the number of times that the watchdog actually has to wake up. So it's...
Right, I'm saying, so expires at is basically like calling cancel and then go through our async wait and reassign the thing.
So yeah, if we call expires at up here, then that would be effectively the same as doing a cancel. Yeah.
Okay, good to know.
So this works. It's, as you say, it's a bit of a blunt instrument. What if we want to do something a little more
fine-tuned?
Fine-tuned. Okay.
Or little more aimed, because what we currently have is that one side might time out, but the other one might still do something. Right. So
right.
You could have a situation, let's say you download a big file, which takes more than 5 seconds. For some reason, your buffer supports that, which I guess would not happen with 1 kilobyte. But I'm just saying, in theory, you could have something still going on and the thing times out.
So, okay, so let's see if we can build to something that treats cancellation in a more fine-tuned way. The first thing to note, though, is that cancellation is actually a fairly hard problem. And the reason for that is that cancellation has an inherent race condition. So if we imagine our code as being structured into 2 separate communicating parts, we have the user code and we have the asynchronous facilities that are provided by the operating system. If we think of it this way, when we run our typical asynchronous operation, we as the user, we send a request to start the asynchronous operation. And the asynchronous operation runs in the background, and when it's complete, it calls back into our user code to tell us what the result was. Right? It's pretty straightforward. Now, in the case of cancellation, what's happening is we start our asynchronous operation in the same way, but then we decide before it's done that we want to cancel it. And then in this case, the operation is canceled and it communicates a result back to our user code that it didn't complete successfully. So where's the race condition? So the race condition happens in this kind of situation where we start our asynchronous read and it's running in the background, and we decide we want to cancel it, but at the same time, it completes successfully. So what happens here is that our cancel misses the opportunity to stop the operation, and we just get the callback telling us that the operation completed successfully. The reason this is an issue is if we simply base our decision to start a new operation on the callback that said it was successfully completed. And if we do that, we're just going to keep going even though we wanted to cancel. So what we need to do to solve this race condition is add some kind of flag in to check whether or not actually we intended to cancel even though the operation completed successfully. So if we go back to our code, Even though this race condition is inherent in cancellation, this code deals with the problem by using the socket itself as a flag to indicate cancellation. And it does that because when our watchdog calls stop here, then stop in turn closes the sockets, and that changes the state. And then our read and write loops, when they try to start the next operation, say here, fail to start because the socket has already been closed. And so they complete with an error.
Yeah, but I mean, that means we're not actually canceling the operation, we're closing the socket, right? I could, in theory, wait and then close the thing once the operation is done.
You could. In Asio's case, closing is a cancellation, but it's a cancellation that also changes state.
What would happen if I just called cancel on both sockets in our existing code?
Well, let's try that. Let's change the code to do that. I'm just going to copy. Okay, so let's change our code to use cancel instead of close. So first of all, we're going to change our stop here to call cancel. Okay, so now we have the problem that we need a flag to detect cancellation in case there is that race between successful completion and cancellation. So let's add a new flag to our class here. We're going to call it stopped, and we'll give it an initial value of false. And when we call stop, we're going to set it to true, like that. Since we can't rely on the socket being closed anymore, we need something to prevent this loop of operations here from continuing. So what we're going to do is we're going to add some tests like that in. That will cause the chain of asynchronous operations to stop.
Why do we even need that? Wouldn't you, the question, because we would have just called it by error. So we would have just, if you cancel, you just get the other, you get an error, right?
Okay, but that's the race condition. You may not get the error. So we're just going to run this. Okay, so we're going to run step 2, and we'll do the same thing. Thing is, there's actually, the race condition still exists in this code, but it's hard to see. And it's actually in the calls to async write. So what async write does is it composes multiple calls to async write sum together. And if it hasn't transferred all of the bytes, then it's going to perform another write to keep going until all bytes have been transferred. But this actually has the problem where if the first write had finished successfully at the time when you issued the cancel, it would still go on to start the next write to finish all of the bytes without paying attention to our is stopped flag. So what we actually need to do here to solve the race condition.
Right. So just to clarify, the async write is, if I want to put it very simply, it's just calling async write sum on the socket over and over again until the buffer is exhausted.
That's right. That's right.
And so if the async write sum completes, then you hit the cancel. Async write will just call the next async write sum, and you might never notice.
Exactly.
Now, this race condition, is that something that only happens if I'm multi-threaded? Or can that
happen? No, so it's actually unrelated to threads. It's a race condition between the parallel chains of asynchronous operations, but you can still have this problem in a single threaded program.
Okay, so if my async write sum completes, the completion token is invoked due to a post, right?
Yes.
And so this means there is a delay. The operation is complete, but the completion handler isn't invoked yet. And if in that time I call cancel, nothing happens. It's basically a null.
That's right.
That is the race condition. And so that means also that the busier my IO context is, or my executor, the higher chance I actually have of running into that race condition.
Absolutely, because your queues grow longer with more events needing to be run. And so the chance of that happening is increased. That's right.
Well, it actually might happen exactly that way, because I have let's say my timer expires at the same time as my async read, a second before my async, a tick before my async read completes. Then it posts its completion handler, that async write posts its own, and the completion handler of the timer then triggers cancel. But at this point, my async write completion handler is already enqueued, right?
That's right.
Okay, it's actually really mean, and not like a very rare one. It might actually happen rather often.
So in the case of async write, we can actually fix this problem by inserting what's called a completion condition, which is a function object that's run in between each of the async write sums. So we can do that here by adding. What we're going to do is we're going to make this completion condition call the default completion condition, but also check whether or not the object has been stopped.
So just why does it return a size t?
So the completion condition function object is actually used to determine the maximum number of bytes to try to write in the next write sum call. And we use the return value of 0 to indicate that the write should stop. So what this completion condition now does is check the is stopped flag. If it's false, then it will allow the write to continue, depending on what the underlying completion condition says. Otherwise, if stopped is true, then it will return 0 and the write operation will finish.
Wait, sorry, gotta help me out. What does the transfer all give? That doesn't mean the completion condition checks the error?
It does actually check the error as well for you.
If there's an error, I get a 0, and if I don't get an error, what do I get back? Or what is the n in this case anyhow?
The n is the input, is the number of bytes that have been transferred so far, and the result is the number of bytes you want to read on the next operation.
Oh, so sorry, transfer all returns the max size t value?
Conceptually, it does. In practice, it actually deliberately returns a smaller value because on certain operating systems, you want to limit the maximum size of your outstanding reads and writes because they otherwise consume what's called non-paged memory. And if you have too many of them outstanding, then you will use a lot of your memory up.
Because I would have just put in the n we get in the we put in the buffer minus the n that's already written is what I would have returned.
You can do that, and that works perfectly well for small buffers. Doesn't work so well if you're trying to write many gigabytes at once.
Oh, because then I'm above the paging size as well.
Yep.
All right, so, because I call this completion condition over and over again, it's gonna be fine, right? Because
that's right. That's right.
Okay.
Yes. So this transfer all gives you some sensible defaults, but you as a user can use a custom function object just like this one to tune how your write operation behaves.
And so if I don't pass in one, it's probably going to use transfer all internally as well?
That's exactly right. That's the default.
Awesome.
Okay, so we fixed our race condition here. We probably wouldn't have been able to see it very easily in our test program, but what we have on the screen now is a complete, correct proxy. Next step 2. Not going to run it again because it's just going to do the same thing.
Okay.
So this program shows you what you need to do to keep track of cancellation manually. My general advice would actually be if you are just using cancellation to shut your program down or terminate an idle connection, then I would stick to close because that will give you the convenient behavior by default. But if you do need to use something like cancel, then this shows you the kind of bookkeeping you need to perform.
It does look a bit cumbersome.
It does. But this doesn't solve the thing that you asked for before, Klemens, which was what if I just wanted to stop one of the operations and not cancel everything? Because we're still canceling all of the operations on the sockets here. Like, what do we have to do to just cancel one of the operations? This is where one of the new features in recent versions of Asio comes into play, which is per operation cancellation. So let's go back. We're going to start with our previous program. Make this step 3.
Right, so I mean, an application for operation by cancellation would be that I say I stop traffic coming in from the client, but I then let it finish whatever it goes downstream.
So what I had in mind is something a bit simpler than that, and that is to use a lack of activity from the server to generate a timeout. To generate a heartbeat to the client, so that the client still knows that the proxy is active, even though the server itself might not be communicating. What I'm going to do here is we're going to change this read operation, read from server, write to client, to have its own cancellation, which is independent from the cancellation of the sockets as a whole. So to start, let's add an extra timer. So we've got our heartbeat timer, and we're going to add a new chain of operations which check the timer. So it's going to look a lot like the watchdog. But what we're going to do this time is we're actually just going to say that the heartbeat timer is going to fire every second. So we're going to send a heartbeat once a second. Once again, we need to check whether or not the connection as a whole has been stopped. The question is, what do we put here when we want to produce a heartbeat? We'll come back to that. And we'll just add the loop back around.
Can you first define what a heartbeat is? Is that like an empty message or?
Yeah, so well, in this case, we're just going to send a dummy string that says heartbeat. Let's write the code that does that next. So instead of writing the data we just received from the server to the client, we're going to write a message. For convenience, we're just going to construct the message straight into the buffer that we would have otherwise received something. And just to make it look interesting, I'm going to send the string heartbeat followed by a count of the number of heartbeats so we can see how many we've sent. And we're going to send it on its own line. We'll just reuse the write to client function to do the actual sending. So that's what we're going to send as our heartbeat.
Okay.
Now what we're going to say is if this operation is cancelled, this read, then we want to send the heartbeat. So we're going to say if the error, let's increment our count so we can see how many we've got. And then we're going to write our heartbeat message instead. So what's going to happen here when our operation completes, our read operation, if there's no error, so it did transfer some bytes, it's just going to write those bytes directly to the client. Otherwise, if the operation was cancelled somehow, then it's going to send a heartbeat. Any other error, everything's going to stop.
If I cancel by closing the server socket, the error would be in a pipe close, not an operation aborted, right?
The error would be something like that, or perhaps bad file descriptor, that kind of thing.
But it wouldn't just be operation aborted.
Could be operation aborted, but your heartbeat's not going to get sent anyway because the write's going to fail because the socket's just being closed. Okay, so this is going to actually send the heartbeat. We still haven't hooked in the code to cancel the read operation. So how's that going to work? So this is where we use a new feature that's just been added to Asio, which is the per operation cancellation. And per operation cancellation uses a signal and slot approach where every operation has a cancellation slot associated with it. And if you want, you can hook it up to a cancellation signal. So let's do that here.
Because if I were to call cancel on the server socket, then I might also cancel the write operation, right? That's why we want to be.
That's right. We want to be more discriminating. So there's our cancellation signal, which is the producer side of the signal. So what we're going to do here is we can now fill this in. We go, we're going to emit the signal. So that's going to generate a signal, and we'll discuss what this argument means later. And then what we need to do is we need to hook our cancellation slot into our read operation. And we can do that up here by using the bind cancellation slot function. And the slot that we're going to bind in here is the one that's associated with our heartbeat cancellation signal. And we no longer need this deadline either, so we just remove that. So what we've done now is we've connected these signals and slots together. So we have our signal, which we can use to emit a request to cancel. And by using bind cancellation slot, we are saying that if that signal is emitted, we would like our async read to be canceled. So let's feel like my run of good luck has been broken.
First time it didn't compile immediately. So to tie it into the last thing, we talked about your overload operator. The overload operators we used last time do all of that implicitly. They construct the cancellation signal, attach it, and do all that stuff.
That's right. What we're looking at here are the low-level building blocks for cancellation. So let's just run our example here. So if we connect our clients,
connection closed by front host.
I know what I forgot to do. Sorry. I need to kick off the chain of operations for the heartbeats. That's what I forgot. Okay, let's try that again. And telnet. Okay. There we go. So we're getting some heartbeats. Now, eventually, the deadline is going to kick in and terminate the whole connection. But in the meantime, that async read is being cancelled and sending us a heartbeat. And then it goes back round and still reads. So if we're quick enough, then it will still transfer the data from the server to the client. So let's take a look at what actually happens when we add the cancellation slot into our example. So we kick off the asynchronous operation just as we did before, but as soon as the operation starts, it assigns a cancellation handler into the slot. Now, this is the handler that will be called if we want to enact cancellation. Now, the operation continues to run in the background. Then we decide we want to cancel. We now emit a signal, and that causes the slot to invoke the cancellation handler, which in turn causes the completion for the operation to be triggered.
And the handler then goes to something implementation defined, depending on what kind of socket IO object you use. Or
that's exactly right. It depends on what the operation is. On Windows, for example, then it's going to be calling the cancel IOX function. If it's Linux using Asio's ePol reactor implementation, then it's going to be calling a function on the reactor to cancel the outstanding operations. The important thing about the slot, though, is that it can only be used with one operation at a time. It's not to be shared with any other operation. But what you can do is recycle the slot and use it for a subsequent operation. And this is actually what you would be doing if you were using, say, coroutines to compose your asynchronous operations. Your coroutine will have the one slot that gets recycled for each operation that it runs.
Does that handle the aforementioned race condition automatically, or would you need to take care of that? That is, if the cancellation signal gets emitted after the first async read sum completes.
So the slot by itself doesn't provide you a solution for the race condition. The compositions on top of the slot do. So a coroutine, for example, would internally have a flag that records whether or not it has been cancelled.
So that is somewhat similar to the isStop flag we have just for cancellations.
That's exactly right, yes.
Okay.
The other important thing about the slot is that if you don't provide one, you don't connect it to a signal, then actually it compiles out completely. So there's no overhead for normal operations compared to how they were previously if you don't supply a slot. So the thing to remember about cancellation slots is that they are a low-level mechanism. Right? They're the low-level building block for cancellation. The idea is when you're writing high-level code, you should probably reach for one of the compositions that takes care of that for you automatically. The coroutines that we saw last time are an example of that. I'm just going to rework our example to use a different mechanism for cancellation, and that's another new feature in Asio as of 1.19, which is called parallel group. So what we're going to do is we're actually going to remove our separate heartbeat loop because we're not going to need it anymore. And the other thing we can remove is the cancellation signal because that is also going to be provided for us automatically by the parallel group. Okay, and now we go up to our read from server, which is where we were previously binding in the cancellation slot. And instead, we're going to replace it with a parallel group call. So a parallel group is composed of multiple function objects that are used to launch asynchronous operations. So we're going to write a function object first that starts our async read operation.
So would it be fair to compare that to what we did last time with the awaitable and the operators in a more generic way?
It is actually what underlies those awaitable operators.
Okay, you mentioned before that the cancellations have no runtime overhead if you don't use them. How is that achieved? Do you have a compile time detection of whether or not the token has an associated cancellation slot? Or
actually, there's both compile time and runtime detection, and depending on what composition mechanism you use, one of them will take effect. So by default, in the Lambda-based code like we've got here, if we do not use bind cancellation slot, then it's a compile time thing. It detects there is no cancellation being used. If we're using something like the coroutines, which naturally type erases the implementation of the coroutine, then now it's a runtime check, and that is detected through the slot not actually being connected to a signal.
Right. Why can't I reuse the signal? Why is it like a single slot?
So the idea there is that this cancellation mechanism should be as lightweight as possible. It should have as little overhead as it can, and that means not catering for synchronization, so not allowing you to register multiple cancellation handlers from different threads, for example, not allowing you to generate, like to emit a signal from a different thread. It leaves all of that up to you. It's the higher level things on top, like make parallel group or the awaitable operators, that will have to take care of that. So the slot is designed for a single purpose, which is to cancel just one operation.
And does it store the target slot in a pointer, or?
Yeah, so the signal object, the cancellation signal object, provides the storage for the handler. So it's actually an implementation detail. The approach I've taken is that it will recycle the memory storage as aggressively as it can for any new handlers that get registered. However, the important point is that actually the cancellation slot is a concept, not just a particular concrete class. So if you have particular needs, you can actually implement your own cancellation slot and associate it with your operations.
So if I wanted to, I could use something like boost signals too, write a wrapper around it and inject that as a cancellation?
I don't see why not. So the thing about parallel group is it will run the operations in parallel, but in order to not discard any information that might be useful to you, even communicates the order in which the operations complete. What we're doing here is we're just going to make a decision based on which operation finishes first. So, and it's index based. The first operation, number 0 operation, is the read.
It's in array because I could have more than 2, right? So I could have like 50 operations.
Yes, in its current implementation, it's a variadic function. So at compile time, you specify how many operations you're going to have. So case 1 is when the timer finishes first. And in that case, we are going to increment the heartbeat counter and then initiate the sending of the heartbeat to the client. Okay, so just to recap what's going on here. So what we're doing here is we're starting a parallel group, which consists of 2 operations. The first operation is our async readsum call, and our second operation is our wait on the heartbeat timer. I just realized something.
So the parallel group means it runs the 2 in parallel and then cancels then waits for one to finish and cancels the second one?
That's right. This is actually configurable through this first parameter here to async wait.
Oh, that's okay. And so that could be wait for all?
There's 4 options here. There is wait for all, which obviously waits for all of them to complete without canceling. Wait for one, which will cancel the remaining operations as soon as one of them completes. And then there's a couple of finer grained ones called wait for one success and wait for one error. And just to point out, though, of course, that this being a function object, you can actually implement your own that are more tailored to your particular use case. At the completion of the operation, so whichever one finishes first, the other one will be cancelled automatically. And the make parallel group takes care of the binding of the cancellation slots into each of these places for you automatically. So you don't have to do it. So you can imagine internally there is a separate cancellation slot for each of the parallel operations. Pressure's on. Need to make this compile first time.
We're going to reactivate your streak here. Damn.
Okay.
Expires after.
Of course.
1 second, it will be 1970, huh?
Well, thankfully, the standard chrono stuff catches that as a compile error because the duration type is distinct from the absolute time point. Okay, there we go. So let's run that. And I think I've forgotten to initialize my heartbeat count, but never mind.
Well, at least it's incrementing. So I have a parallel group. can I associate the completion handler of the parallel group with another cancellation slot?
Yes, absolutely. A parallel group, it's a composed operation, and the composed operations in Asio all support training of these cancellation slots.
And so the parallel group internally takes my cancellation signal and then fans it out.
That's exactly right. And so this is part of the reason why cancellation slot as the building block provides no synchronization at all. So to be as lightweight as possible, but something that might introduce the need for synchronization, like make parallel group, that's where the responsibility lies for ensuring things are correctly synchronized. So it will take the signal that's generated and then correctly disseminate that signal out to the parallel operations that are within it in a thread safe way.
But that also means like if I didn't care about that, I just stuffed like a few parallel groups into other parallel groups into other parallel groups, I wouldn't need to worry about any of this cancellation, except for the fundamental first one, basically.
That's right. You can completely ignore cancellation slot as a thing if you can build your entire operation out of something like make parallel group. So, and actually, I would recommend that as an approach, that if you can model your program shutdown as an extra operation within a parallel group, then you can just use that to automatically trigger the cancellation of the other part of the tree.
Right. Any idea what one could use for such a shutdown?
Well, actually, that might segue quite nicely into our next example. Probably want to use a signal, and by a signal I mean a POSIX signal like SIGINT, SIGTERM. But as of the recording of this video, Asio doesn't actually provide built-in cancellation support for waiting on signals. So how about next, let's use that as an example of how to incorporate cancellation slots into custom asynchronous operations.
So it seems to me like the easiest way to achieve that is I have the signal set and just put that into the parallel group.
That's right, exactly. As of now, that is not supported out of the box. So let's make that work. I'm going to start a new example here, and I'm going to copy in one I prepared earlier. So this example is just to show a very simple wrapping of a weight on a signal set. But to make it a little bit more interesting, what we're going to do is we are going to translate the integer signal number that we get back from the signal set into a string that tells you what the signal was. This is a custom asynchronous operation, currently does not have any cancellation support. Starting from the top, down in the main function, we're doing exactly what you were just talking about here. We have this coroutine here, which is called timed wait for signal. And internally, it's doing a co-await on two operations that are running in parallel.
So now just to be clear, this is basically shorthand for the parallel group we just used.
Yes, it is. That's exactly right. Those operators, logical and logical OR, are built on top of parallel group.
Okay, the timer async wait has support for cancellation slots.
It does.
So we can just use that out of the box in case the signal comes first, but we want to add it for demonstration purposes to the async wait for signal.
That's right. Okay, so let's just go back up here to our implementation of async wait for signal. This is a fairly standard custom asynchronous operation. Not that many people would ever be implementing these, but if you need to, this is the pattern. We have our function, which we call the initiating function, which is what the user will call to start the asynchronous operation. Now, what an initiating function needs to do is it needs to call this Asio async initiate here. And this is the thing that will actually kick off the operation for us. And the arguments we pass to this are, first argument is a function object, which provides the concrete implementation of the operation. And then after that, we pass the completion token that's going to be called.
So where's the async initiate usually used? Because I mean, it's not in the detail namespace, but it's not really like a popular thing to do.
So it's specifically for implementing low-level asynchronous operations. So if you looked in the Asio source code at the implementation of, say, async read sum for a socket or async wait for a timer, you would see a call to async initiate. For anything higher level, you're probably building on top of one of the composition mechanisms like coroutines or async compose.
Okay, so async compose is if I want to combine several operations into a composed operation. Async initiate is what you use internally for a single asynchronous operation.
A single asynchronous building block, that's right.
if I get this right now, time if I do, I put in the token here.
Yes.
This token, this is what we talked about, which is basically any token that has some other template magic defined. And the async initiate turns that into what up here? Something callable. Oh.
That's right. It turns it into a callback, a function object that has the signature that's just a couple of lines above there. This one here. So it is a callback that will take an error code and a standard string.
And so if my token is something like user awaitable, I get a callback to resume the awaitable.
That's right. That callback is an implementation detail inside Asio's user awaitable, and it takes care of marshalling the result value back into the coroutine and then resuming the coroutine.
Okay.
So first of all, we need to get the executor that the result's going to be delivered on. Then we're going to create this intermediate handler, which is the one that's going to be passed to this underlying signal set's async wait. And this handler takes the signature that is produced by a signal set, which is here, which is the error code and an integer signal number. And then we're going to just translate it into a string representation of that signal. The final thing is to call the user's handler with that transformed result.
Why do you pass on the second executor here and to get associated executor?
So that's to provide a default if the user hasn't specifically set an executor for their handler.
So that's the case for stuff like lambdas.
Exactly.
What would happen if you didn't provide it?
Then right now the default is what's called a system executor, which is one that essentially can run the handler as an inline call or on a system thread pool.
So if you didn't, so you're defaulting to the executor of the signal set. If you didn't, the thing might run on a different thread.
It could, yeah.
Okay, number 2 is, why is this mutable?
It needs to be mutable so that we can move the handler at the bottom here.
This one.
It's necessary for us to turn our handler object into another R value when we call it.
Because a handler can be R value qualified, so you only invoke it once. Is that right?
That's right.
Let's quickly step through that one more time. We have this intermediate handler. It translates the insect number into the final handler we pass in here. So we have like an intermediate step. So that's why it's intermediate handler. That makes sense. Now my question is, why do we bind the executor here?
Ah, right. Yes, we didn't talk about that. We want to preserve the user's intention to have their handler run on a particular executor. So,
and the 6-set async wait doesn't do that internally,
unless we tell it what the user's user's executor was.
The reason, sorry, I missed it. The reason you do that is because the intermediate handler again is a lambda.
Yep.
So it doesn't have an associated executor. So you're associating the executor of the handler with the intermediate handler down here.
That's exactly right.
Yes, I missed that point.
Okay, so before we add cancellation support in, let's just run this to see what happens without cancellation support, just so we can prove that it makes a difference. So let's make step 5 has no arguments, I think. So it's just going to, if we go down to the bottom here, see what it does. It's going to run the async wait for the signal in parallel with the timer wait, which is going to be 5 seconds long. All right, so what should happen is if we just run it, then it would stop after 5 seconds unless we somehow send it a signal before that. So if we run this, so if I run it first and I just do a Control-C, then it's finished pretty quickly, and you can see it's printed out the name of the signal there as sigint. And so now what I'm going to do is I'm going to run it again, and this time I am not going to press Control-C. We wait 5 seconds. Okay, so you can see from that output there that the timer has finished, but our program's still running, and that's because it's unable to cancel the wait on the signal set. Okay. And as you can see, as soon as I did the Control-C, then that actually triggered it to finish, and you can see it's printed timer finished first there. Okay, so let's add our cancellation support in. So the first thing is that cancellation slots are actually a bit like executors in that they are associated with your handler. So the first thing we need to do is to ask the handler for its associated cancellation slot. And just as we did with get associated executor, we're going to pass in the handler, and then we're going to pass in a default. And this default is a default constructed cancellation slot, which means that it's empty. It's not connected to any signal. Now, what we do is we want to register our handler that knows how to cancel our operation. And we should only do that if our cancellation slot is connected to a signal. So we first add this test if cancellation slot is connected. And now we're going to assign a handler into the slot. We're going to pass a reference to the signal set. Now, all cancellation handlers take a type, which is the type of cancellation being requested. We're not actually going to use that here. We'll talk about that later.
You said before that this can be a compile time decision if it's used or not. So that looks like runtime.
This one is a runtime decision. That's right. If you wanted to make it a compile time decision, it's a little bit more involved. What you need to do is test whether or not associated cancellation slot is going to produce something other than some arbitrary default that you pass in.
Okay. That's how you do that.
Okay, so that's it. That's all we need to do. All we need to do to add cancellation support is first ask for the cancellation slot for the handler. And then if that slot is connected, we're going to assign our cancellation handler into it. And that cancellation handler, in this case, just calls cancel on the signal set. And we're going to make step 6. So first let's run step 6, and I'm going to press Control-C after a few seconds. Okay, that's as it was before. Now let's run it. I'm not going to press Control-C. We just let it run for the 5 seconds. And there we go. The operation was cancelled.
So you also can see the dot cancel logger. Is that from the cancellation slot in your handler tracing here?
That's right. So this call here corresponds to our call to sigset.cancel.
Yeah.
The other calls at the bottom, though, are actually from the destructors of the deadline timer and the signal set.
Okay, makes sense. But now we're again a bit blunt here, and then we have a cancellation type, and then we just call sigset cancel, whatever the cancellation type is. And we haven't yet discussed what those types are. So maybe you want to go over that now.
Sure. Okay. So the first thing to remember about cancellation is it's not just about asking an operation to stop. You also need to know about the state of your object after your cancellation was successful. If the only cancellation you've got is a destructive cancellation, like we saw very early on where we were using socket.close, then you can't do any further operations with your object. That's it. You're done. If we want to be able to perform more operations like issue another read from our socket, then we need to know that our object is still valid. And so this is where the cancellation types come in. So there are 3 types of cancellation in Asio. Well, technically there's 4 if you count no cancellation, but there's 3 that actually are associated with cancellation of an operation. And those are terminal, partial, and total. So terminal, first of all, means that your operation had some side effects, even though you canceled it, but you don't know what those side effects are. So the only safe thing you can do next really is to destroy your object or close it to save its socket.
All right. So terminal cancellation. Can you give an example for that?
A common example might be if you are using some kind of message framing protocol, say with WebSockets or Fix protocol, anything where there's some kind of message header followed by a message body. And so your protocol is stateful and you're reading bytes off the wire. And if you're canceled at any particular point, you might actually be halfway through a message. And at that point, it's not possible to simply start another read of a message because you don't know how far you got through. Right? So that's terminal. The only safe thing at that point is actually just to close your object.
Okay.
So the next,
so that would apply to streams and stuff like that, right?
No, so that's where partial comes in. So if your thing is actually a stream of bytes, then you can actually know a little bit more about the state of your object. If you cancel, then you may have transferred some number of bytes, and the value that's passed to your completion handler tells you how many bytes there were transferred. So you actually know what you can do next with your object. If you were trying to download a 1 gigabyte file over HTTP, and it got cancelled at 900 megabytes in, that would be the number that's passed to the completion handler. And well, if I'm going to start this operation again, I should only ask for the remaining 100 megabytes. Right? So that's partial cancellation, where you know something about the state of the object.
Right.
So the final type is called total cancellation. And what that means is if the cancellation was successful, then the operation had no observable side effects. What you can do then is follow that up with a call to the same operation again, potentially, and that's going to be safe. So this is the strongest guarantee for cancellation because it's like a complete rollback of any side effects.
The signal set we just used would also count as total, even though you missed the signal because you don't have side effects?
That's right, because yes, so that's the second example here. Wait for readiness is an example of something that supports total cancellation because it has no side effects on its own. The other examples we have are the low-level system calls like read sum and write sum, or the system calls that underlie that, are also examples of total cancellation because their contract is they either transfer 0 bytes or non-zero bytes. There's no partial state for them. If you cancel them, then they will return 0. There was no bytes transferred. If they transferred any bytes at all, then they're considered to have succeeded and not been cancelled.
And so the partial would apply to the composed operations like async read until or stuff like that.
That's exactly right, because they compose consecutive async read sum operations together. You could be cancelled at any point in that chain, and you've already transferred some number of bytes at that point. So that's why that's partial.
If I have an async accept and I cancel that one, is that total? Because even though I might have rejected a connection, I don't have side effects in my code?
Yeah, there are no side effects that you can observe in your code.
Right.
So I think that's the key point, that you can't, from the outside of that class, see that there was a side effect.
Right. So that the side effects means my IO object is again in a state that I can just repeat the action without taking anything into consideration.
That's
the partial means I need to take stuff into consideration, but can restart. And terminal means, well, terminal, it's just I can't do anything anymore.
That's exactly right. So I thought what we might do next is add cancellation in to an example of this last point, which is some kind of fully buffered message framing. So this is an example of providing total cancellation on top of lower layers that don't support it, where you are allowing people the ability to repeat the same operation, and you make that possible by buffering, and so preventing the side effects from being visible through the API layer. As a starting point, I'm going to use a program I prepared earlier. Okay, so this is a simple coroutine-based program which reads messages from a socket. So the main part of the handling for a client is here. And this is a loop which reads a single message from the socket ultimately and just keeps doing so and printing it out. The signal for when there's an error, like there are no further messages, is simply that the string returned as empty, just to keep things simple. Right. So it's going to keep running forever until it gets an empty string back. So if we just compile this just to demonstrate. Okay, so we're going to run 7. Okay, so if I go down here, so I'm going to telnet. The delimiter, I should have mentioned this, the delimiter for our message is actually the pipe symbol, just there. So if I type a bit of garbage, just hit return.
So the thing gets cancelled by either an empty message or by an error?
The operation completes.
Yeah, that's what I meant.
Yes. Okay, so at the moment, so we saw some activity, but that's because this operation is implemented in terms of async read until, which is just going to restart the underlying async read sum operation until it finds the delimiter, and it hasn't found it yet. So now I'm going to put in a pipe. So we can see here, it's just now printed out that it's received a message. There we can see that we just got a few messages printed out there. What we're going to do is we want to say that this operation is cancelable, which it already is because you get that for free when you use the coroutines. But we also want to say that it supports total cancellation, Now, that's not something you get for free with the coroutines. So the thing about terminal cancellation is that it's the only type of cancellation that is implicitly transitive. Because it's the weakest guarantee, if you're composing things, you know that if they support any cancellation at all, they're going to support terminal cancellation. It's the only one that's safe to assume is present.
And the reason we can do total cancellation is that we just assume our protocol allows us to drop message frames.
Well, so actually it's not the protocol here, but actually that we are reading our messages into this buffer, which we store between operations. If we get cancelled, we're going to leave our partial message in the buffer, so that if the user then calls read message again, we'll be able to just pick up whatever has been transferred so far and use it for the next operation.
And the dynamic buffer guarantees that we always append at the end.
It does. And we have to actually explicitly extract the message from the buffer, which is what this bit is doing here.
All right.
So let's add support for total cancellation in here. As I said, by default, you get terminal cancellation, and that capability is encoded into the cancellation state, which is held within the coroutine. So what we need to do to customize this is actually to replace or reset the cancellation state for the coroutine to do something different. So the way we do that is we call this reset cancellation state function. Okay, so it's going to take an argument here. Now, this argument is what we call a cancellation filter. So it's whenever our caller emits a signal asking for us to be cancelled, it's going to be passed into this cancellation filter. So I'm going to say whatever got requested is here. And then this function object needs to return the actual cancellation type that we are willing to support. The default is to ignore anything that's not terminal. Let's code up what the default behavior is just to illustrate.
Can I return something that tells the caller that I don't support any cancellations?
You're not really telling the caller that you're not, but you're simply ignoring their request. And to do that,
the return value gets forwarded.
It gets forwarded downwards, right? So if I did this, then I've completely disabled cancellation. Right?
So the use no throw awaitable, the completion token forwards our filtered cancellation type. That's right. You could also go the other way. Is that correct that you say, well, whatever cancellation comes in, I just make everything terminal?
You could do that, yes. And in fact, we are kind of doing something similar here. Because what we want to do is we actually want to support total cancellation, but we're building our operation on top of something that doesn't necessarily support total cancellation, may only support partial cancellation. To make that work, we're just going to say, so cancellation type is a bit mask. So we're going to say if the user is asking for total cancellation, we're going to translate that into partial cancellation for the underlying operation. If it's any other kind of cancellation, because keep in mind total is the strongest guarantee, then actually we're just going to pass it through as is. So the key thing here is that cancellation type is a bit mask, which represents the kinds of cancellation that the user is asking for, and they can ask for multiple kinds. And if they're asking for multiple kinds, you should interpret that as saying, please give me the strongest guarantee you can within the bit mask that I'm requesting. And then as the operation, we look at that bit mask and go, well, actually the maximum we can support is partial or terminal, in this case, total. And we can then make that happen. Make that cancellation.
How does the user, if the user gives you a bit mask with all of them, how does he find out which kind of cancellation was applied?
By inspecting the arguments that are passed to the completion handler, because that will tell them what happened.
So for example, if I had a partial and async read until, I would know because n is unequal to 0, right?
That's right. So actually async read until doesn't support total because at some point in its life cycle, it has a partial state, right? So it can't support total for that reason. And we're adding total in this higher layer because we're taking that partial state and putting it into a buffer as a data member for next time.
Right.
After the operation completes, we want to check whether or not the operation was cancelled. So because again, we have to deal with the fact that there's the race condition. This cancellation state dot cancelled tells you what value is actually saved. So in this case, it'll be the value that's passed through our filter. At this point in the code, we only care that it's not none, that there was some cancellation request. And so in that case, we're just going to return an empty string. Now, to be a good citizen, what we're going to do afterwards, though, is turn our cancellation state back to its default.
Why do we return an empty string on cancellation and whatever is in the buffer?
Well, because what is in the buffer at this point may not be a complete message.
Okay, so we basically don't support partial.
That's exactly right. We're going to just provide total semantics, total cancellation semantics in this function.
Okay, so we got total meaning basically, yeah, but you can read some more, but the input is going to be, the previous input is going to be ignored, or we have a terminal one.
If we go back to the cancellation types, a stronger guarantee, right, is kind of like a subset of the weaker ones, right? So if you ask for terminal and you happen to get total, well, you still got what you asked for. Likewise, if you ask for partial and you got total, right, you asked that your object be in a particular known state after cancellation, and you got that. It's just that it happened to satisfy it with a stronger guarantee.
Right.
Okay, so what we'll do, we'll just go back here. I'm going to change our simple read here into a couple of parallel operations. So first, I'm just going to copy a function that we used in one of our previous examples. So this was a simple coroutine that just waits for a timer to complete. Okay, so now we're going to start two operations in parallel. So the first operation is our read message. Our second operation is going to be a 5-second timeout. And now, as before, we need to check what result finished first. So if it's index 0, then it is our read that finished first. And then if the timer finished first, well, let's just print out that it timed out. So if we just, right, this is step 8. Okay, so we're just going to run step 8. So what should happen now is we run it, and every 5 seconds, if it hasn't got a message yet, it's going to just print timed out. But then it's going to go around the loop again, and it's just going to try to get another message. Okay, so I'm not going to do anything for 5 seconds. Yes, so we didn't type anything for 5 seconds, and so we got a timeout up there. So if I run it again, right, let's just watch it again. We'll get, so we got a timeout printed there. So now, and there's another one. I'll type something with a pipe. Right, now it's printing our message saying received. Again, now we're not getting the timeout because I keep sending it new messages. Right, but if I now wait 5 seconds, there we go. We've got another timed out. So just to recap what was happening there, we've got the read and the timeout occurring in parallel. Right, so if the read finishes first, then the timeout's just going to be cancelled. The more interesting thing is what happens when the timeout finishes first. So in that case, the read is going to be cancelled. It's going to emit a signal into the cancellation slot for that coroutine.
Which cancellation type would it pick as a default here?
The default is always all the bits set on.
Okay, so that basically means give me whatever you can.
That's right. Give me the best that you can. And yeah, so then that cancellation request is going to come into the filter that we've installed here. And if it includes cancellation type total, right, then it's going to translate that into cancellation type partial, which is then forwarded on to the underlying async read until.
Alrighty.
So that's cancellation in depth. A reminder that the code for this talk is available at the link above, and you can download the latest versions of Asio at the link below. And just again, noting that the code shown here uses features from Asio 1.19 and later.
And when does that reach boost Asio?
That will be in the boost 1.77 release.
Which comes out when?
I think it comes out in August 2021.
Nice. So pretty close there too.
Okay, well, thanks for watching.
Thank you very much.
Till next time.
Till then.